Good day everybody. In this video I would like to talk about ground movements of reactive soil and how we can estimate it. So reactive soil is very plastic material that shrink or swell a lot depending on the amount of water in soil mass. And I've done a video about this type of material, so please watch it so you can get a little bit of better idea what this tutorial will be about. Let's now look at this diagram and I will explain the procedure that we're going to use later. We're going to do an example. So in this case, we have very thick layer of reactive soil, and we can divide it into stable part and active part. So this is active and stable. Well, how do we do that? Typically, we do some site investigation and see what part moves, and we'll also look at the changes in the water content and suction so that we can easily define this boundary between active zone and stable zone. So once we do that, and well, if we don't have any data, I'm going to give you advice how to draw the line between stable and active zones. So the procedure deals with this active zone. And the active zone can be divided again into two parts. So this will be cracked zone. You see this is cracked. And this one is uncracked. So both parts, cracked and uncracked zones, will move. Maybe during change in the season when we have lots of rain or when we have a very dry period of time. So but cracked zone will typically move more. Because there will be a greater change in suction and greater change in water content compared to the uncracked zone. Why it's called cracked is because you see these cracks on the surface, and through these cracks air can go inside or water can go inside, and it can cause more changes in this part of the soil profile. How do we get this line between between uncracked zone and cracked zone? Again, we will need to do maybe some field monitoring and see what parts of the soil profile changes, which one doesn't. If we don't have this information, and for the example that we're going to do today, we don't have this information, we're just gonna go with the values that were advised, so based on empirical correlations and the data that we have obtained in the past several years. Okay, so now let's see how we can estimate the movement. So this is the formula that we use. So I'm going to explain the formula first, and then I'm going to show you soil profile, and then we'll do the example. So in this case, you will see that we're going to go through the whole thickness of the active zone. So this HS means thickness of active zone. So active zone. And then we have this value alpha. So for alpha, if we deal with cracked zone, so this top, we're going to use 1. If we use uncracked zone here, in this case, we're going to use this definition, which is 2 minus z divided by 5, and where this is depth of centroid. So then we have this value, this index, Shrink-Swell Index, and this index that, well, usually like we need to get it from the field or laboratory investigation, mostly from the laboratory test, when we do swell test and we do shrink test. If you don't have that one, I believe there are some correlations. I've read some literature. There is some correlations between this index and soil plasticity, so you can probably roughly estimate this value. Next one, it's a change in the suction on the surface, so that's the value. And the final component is the thickness of the soil, and I will show you how we get this one. What I'm going to teach you, it's come from this Australian standard, which is AS2870. But if you're from a different country, you can still use this concept, this idea, and I will show you how to select values. So now let's look at the example that we're going to do. So this is the soil profile, and 1 meter from the top is dark brown clay, and we see that this clay is very reactive. It has high shrinkage percentage, 8.75, and swell 2.35, And below we have another clay, probably a similar type of clay, and the values of shrinkage as well also quite similar. So it goes all the way to 3 meters, and we're gonna estimate how much movements is gonna happen during this change in the season in this soil profile. So I'm gonna go to the next slide to explain it. But before I'm going to the next slide, this is the formula that I forgot to mention. So this is how we estimate the Shrink-Swell Index in percentage. We need to know how much swell and how much shrink happens to the soil, and we will divide by 1.8. So that's the formula, and I will show you later the calculations. Let's go to the next slide. Okay, this is the next slide. We'll show you why we're actually doing that. The whole idea is to better characterize the soil, and once we estimate this ground movements, so usually it comes in millimeters. So these are the movements from our estimation. We can assign a class to type of the soil that we deal with, and based on that we will see if we need to do something about the soil, or actually that's not really gonna swell or shrink a lot. So you see that this class A, probably it's the best class when we have sand and rock, and as you know, sand or rock, they don't swell or shrink, so there is not going to be any movements. So then we have, if we have movements less than 20 millimeters, we're going to call it slightly reactive clay. And then you see as the amount of movements increase, it's going to be moderate, then highly reactive, and so on. This one is extremely reactive site. So in this case, you would expect movements of 75 millimeters. So this is comes from the standard for light weighted buildings, the one that will generate stress of about 20-25 kPa on soil. So it's not for high-rise buildings, it's for maybe like 1-2-story buildings. Okay, so now let's see what else, what kind of useful information we can get from here. So this is the data for different cities in Australia. So you will see Adelaide, Brisbane, and Melbourne. So this will be the change in suction at the surface, and you see for all cities the recommended value is 1.2 pF. If you don't know how to get PF, just watch my other video. I'm gonna put a link in the description so that you can know how to convert suction in kPa to these values in PF. And this one, depth of this active zone. So these values are recommended. If you don't have any data, you don't do any site investigation to actually precisely estimate the depth, you can use these numbers. And I will show you later what number we're going to use. So this is just kind of would give you some idea based on the previous investigations. And another thing, this one is a little bit more general. So this is for different countries, not only for Australia. So in this case, you might ask me, well, I'm from like a different country, how I'm going to select this value of HS, right? So these are some recommendations based on this index, zone weight moisture index, so that you can calculate the index. I don't have any video yet, but I probably make a video how to calculate this moisture index, or maybe based on the type of climate. You can estimate the this depth of this active zone. Okay, and before we go to the example, again for Australia, this is suggestions, recommendations. Again, this is very general. If you have some specific sites data, then you're going to use the specific site data. If you don't have anything, the recommendation is that for Adelaide and Melbourne, the depth of the active zone will be, the depth of the cracked zone will be 0.75 of the depth of the active zone. And for other parts of coastal Australia, including Queensland, you can use 0.5 H. So this is something if you don't know and you need to do this procedure, so then this is the value that you're going to use. If you have something from previous investigation, just like use more accurate values. Okay, now let's go to the example and let's do it together. So this is the soil profile that I showed you before in my first slide. What I only added is that the soil profile from Melbourne. And these are the two types of clay, and we have all these values of shrinkage and swell. And these are the formulas that we're going to use from the standard. I already explained them. And these are my calculations. So I will explain how I get all these values, and you see in the end that will be lots of settlements. Sorry, not settlements, movements. We don't know if it's going to be settlements and maybe also swell. So now let's do this example together. Usually we're gonna schematically show suction profile. So if we just, this will be the depth. This will be ground surface, is going to be 0. And we know that for almost all cities in Australia and for probably like other countries, the recommended change in the suction on the surface will be 1.2 pf, and I showed you before in the table. So that will be here. And if we connect this in a triangle, so this will be suction profile. So this is the suction profile that we're going to use to get this average suction values. So this is where we get this. Now we're going to define the boundary between cracked and uncracked zones. So this is Melbourne, and if we don't have any other information, this is going to be 0.75 times H, and we don't know H, so this will be H, and we don't know that because we don't have any site data, but we know that it's recommended that for Melbourne conditions, H should be 2.3 meters. So this is something that is recommended for us to use. So this will be 2.3 meters. Then in this case, the boundary between cracked and uncracked zone will be 0.75 times 2.3, and that will give us here, I'm going to write it here, 1.725 meters. So this is the boundary. Now what we can do also say this will be 1 meter, so that will be this brown clay, and the rest will be this, I call it gray clay, from 1 meters to 2.3 meters. Okay, so this now let's do this change in the delta Z, how I got it. So in the first case, we're going to divide it, will be first layer, because it's just the whole brown clay. So in this case, it will be 1000 millimeters from depth 0 to 1 meter. Then you see this gray, very stiff clay, it's actually divided into 2 sublayers, even though it's 1 layer of clay, but because we have boundary between cracked and uncracked zone, so that will be the first part that we're gonna analyze, and then will be the second part. The reason why we draw a line in difference is because the value of alpha is going to be different. So that's why we actually need to divide it into 2 parts. So if we go back to that first layer of brown clay, so here you will see that it will be 0.5 meters in the middle of the clay layer, and we're going to get this value of suction, and we're going to estimate that. Well, the way that I did is I look at this triangle and at this bigger triangle, So, and then what if we have this value as x? I wrote that 1.2 minus x divide 0.5 meters should be the same as, because it's a part of one triangle, so we have the whole 1.2 divided by the whole 2.3 meters. So that's for this little triangle, and this is for the big one. So it's going to be the same angle, right? So in this case, I got that x it's equal to 0.989. So sorry, 9.39. So these are the value that's got here. Okay, so you can do the same thing for second layer. For this one, you're gonna get somewhere in the middle here, and in the middle will be a value of 1.3625. So it's and for this one, then in uncracked zone, the middle, my estimation gave me 2.013. So you're gonna find also a section for these in the middle of these two layers, and you can check with my values. Okay, so next one is that value of alpha here. So for the first here, for the first layer of brown clay is going to be 1, and for this half top of the second layer above the uncracked zone is going to be 1, 2. That's why I have 1 here and 1 here. So this layer is already inside the uncracked zone. In this case, we need to use the formula, and the formula will be 2 minus c, which depth is 2.013 divided by 5. That should give value about 1.6. So that's what it goes here. So that's for the uncracked zone. Okay, now we're gonna get this swell and shrink values. So let's just do for the first depth of from 0 to 1 meter. In this case, we're going to use this shrinkage and swell values. So I'm going to write here ISS, it's equal. First, we're gonna get the swell. It will be 2.35 divided by 2 plus here will be next one will be 8.75, which is from shrinkage, and divide by 1.8. So that should give you in percentage 5.51%. So that's the value. Okay, so you do the same for this layer and this layer, and you're gonna get these numbers. In the end, we just put all the numbers in the formula. So this is the formula on the values of the values you have. So you see that the answer we're going to have in millimeters is because this thickness of the layer I put in millimeters, and usually we get the answer in millimeters. And when we calculate, you will see that that will be a movement for the top layer from 0 to 1 meters of the brown clay, and then that gray clay above the uncracked zone, it will move 18.9 millimeters, and the estimation that the same clay but in the uncracked zone will move 7.3 millimeters. So altogether will give us 78 millimeters, and in this case 78 millimeters will be very high value of movements. You can go back to the previous slide and look at the table. You will see that it's more than 70-75 millimeters. So this is very reactive soil, and something needs to be done before you go with some construction of lightweight buildings there. Okay, so that was explanation of the procedures, how to estimate the settlements. I hope it was useful to you. Have a nice day. Bye.